In this video, we're going to take some class notes on single versus double replacement chemical reactions. Now, I don't have the term chemical reactions here, but both single replacement and double replacement are in the category of chemical reactions, where you are starting with a group of atoms that are connected in a certain way, and then we're pulling those atoms apart and putting them together in a different way. The first group that we're going to focus on is single replacement chemical reactions. In single replacement chemical reactions, we have a certain pattern that's always going to take place. And the pattern that we're looking for that's going to take place is we are going to have some substance A by itself, and we're going to be reacting it with some compound. I think the book uses the letters B and X. So some two atom compound, two different elements, I should say. And the question is A going to come in and replace B? And if it does, what will happen is the A will go with the X, and the B will go by itself. So A will come in and replace B. That's why it's called a single replacement reaction. For this to happen, the question that we have to ask ourselves is A going to replace B? And how do we know if A is going to replace B? Well, what we have to use is either a metal reactivity series or a halogen reactivity series. Now, in this case, we're looking at the pattern of a metal replacing another metal. If this was a halogen, it would be replacing the second element here, not the first. But in this pattern, a metal is going to replace another metal, and what we look at is this metal activity series. We're looking to see if A is more reactive than B. If A is more reactive, which means it's going to be higher on this list, if A is more reactive than B, then A is going to replace B. B will be sent out by itself, and A will then be connected with X. So what we look at for single replacement reactions is we look at the metal activity series, the metal or halogen. If you're talking about a halogen replacing another halogen, activity series. And specifically what we're looking for is this. Is A, substance A, more reactive? And the way we find out if it's more reactive, higher on the list. Than B. So you're looking for A to be higher on the list than B. That's for a single replacement reaction. Now what we're going to be doing is we're going to be transitioning into looking at double replacement chemical reactions. We're going to go through the exact same process with double replacement chemical reactions. We're going to put a pattern down. We're going to find out what we actually look at, and then how we analyze it to see if it's going to happen. So the pattern that we're going to look at for double replacement reactions is we're going to start with two substances connected. Notice that it's different up here. Single replacement was the substance by itself. Double replacement are two substances that are connected, reacting with two different substances that are connected. So an AX and a BY. And then the question that we're going to ask ourselves is, will A stick together with Y, or will B stick together with X? Notice I write B first because in this case B is going to be the positive and X is going to be the negative. And of course A will be the positive and Y will be the negative. So in this case, we have two substances that we are reacting to form two other substances, a double replacement. A goes with Y and B goes with X. And what we're going to be looking at, the idea of double replacement reactions is there is a certain strength in the connection of A and X and a certain strength in the connection of B and Y. We want to find out if either of these connections, the one between A and Y or the one between B and X, is stronger than either of these two connections. And if it is, then the chemical reaction will take place. So what we're going to look at is not the metal activity series or the halogen activity series. What we're going to look at is the solubility table, or sometimes called the solubility chart. And this solubility table or solubility chart will allow us to know whether that substance will dissolve or it won't dissolve. So I want to spend a little bit of time talking about solubility. So for instance, here is an ionic compound, a representation of an ionic compound, where we have a metal that's bonded with a nonmetal forming an ionic crystal. Here's a metal forming positive ions. Here's the nonmetal forming negative ions. And it creates this positive and negative ionic crystal structure. Positive and negative ions forming an ionic crystal structure. This is the structure of AX. This is also the structure of B and Y. And these guys are forming a metal with a nonmetal, a metal with a nonmetal, the metal losing electrons to the nonmetal, forming an ionic crystal. When this ionic crystal is placed into water, what we know is that water pulls the ions apart. So a positive ion, the negative side of water, swims in and starts to tug and pull on the ion, and it pulls it away. This is called the dissolving process. When we place salt into water and it dissolves, this is what's taking place. The ionic compound is getting pulled apart into its individual ions as we sit there with the spoon stirring the salt and it's dissolving. This is exactly what's happening. The water is coming in, the negative side pulling on the positive ion, pulling it away. The negative side, or sorry, the positive side pulling on the negative ion, pulling it away. And while we're stirring with our spoon, it's getting pulled apart into its individual ions, and we say that it has dissolved. That's the dissolving process. If something has dissolved, we say that it is soluble. If it won't dissolve, we say that it's insoluble. We have a chart that will show us whether something will dissolve or it won't dissolve, and it's called the solubility chart or solubility table. The way that we read this chart is, if it says SOL, it means that it's soluble. soluble indicates that it's going to dissolve. If it reads INSOL, that means it's insoluble and it will not dissolve. What we're going to be looking for in double replacement reactions is we're going to be looking for one of the products, either AY or BX, to be insoluble. If either one of these products are insoluble, that means the reaction will take place. Remember, for single replacements, what we were looking for is A higher on the list than B. And if it is, then yes, this reaction will happen. Otherwise, we would write no reaction. But here, we're not looking at the metal reactivity series for double replacement. We're looking at our solubility chart. So we look at our two substances here. We find them on our chart. If either one of them is insoluble, then we know the reaction will take place. If they're both soluble, then we would write no reaction. So we're looking for is AY or BX insoluble on the solubility table, which means that it will not dissolve. It will stay as an ionic compound, not separated. That means we would drop this ionic compound into water, we would stir, 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 and it would just stay together as an ionic compound. If it's insoluble, it will not dissolve. It will not separate into its individual ions. So based off of that, what I would like to do is cover a little bit of terminology regarding solubility and insolubility. So just some terms that we need to understand moving forward. So first off, the first term that we need to understand moving forward is the term soluble. The term soluble means that it's the substance will dissolve. The substance will dissolve into ions, into its individual ions, forming an aqueous solution. So the substance that we're dealing with, if it is soluble, that just indicates to us that it will dissolve into its individual ions, forming an aqueous solution. The symbol that we use when this happens is AQ. The symbol we use is AQ. If we're talking about something that is insoluble, this means the substance will not dissolve in water and remains together as an ionic crystal It remains together as an ionic crystal that we call a precipitate. That term precipitate means that it will not dissolve. So the symbol that we use when this happens is, in parentheses, we put an S. Now we have to be careful. This can be very, very confusing because when it's soluble, we write AQ. When it's insoluble, we write an S. And the reason being is that S stands for solid. It will not dissolve, so it remains as an ionic compound in the water. It remains together as an ionic crystal. The water's trying to pull it apart, but it will not pull it apart. So it remains as a ionic crystal, a solid ionic crystal. But we have to be careful because a lot of students think soluble, so they think S and go, oh, I'll put an S down. That is incorrect. If it's soluble, it will dissolve and form an aqueous solution. If it's insoluble, it'll stay as a solid, so we put an S. I hope this helps in understanding single and double replacement reactions.